This is a video from section 8.1. If f prime is continuous on the closed interval a to b, then the length of the curve y equals f of x, where x is between a and b, is given by L, which is the integral from a to b of the square root of 1 plus f prime of x quantity squared dx. Now, in Leibniz notation, we can write L equals the integral of from a to b of the square root of 1 plus dy dx quantity squared dx. So at the end of the day, what's happening is I'm going to take the derivative of the function, I'm going to square it, I'm going to add 1, and then I'm going to take the square root and then integrate that result from a to b. So it's literally what's going to happen. Okay? Now, so the directions say to find the exact length of the curve. So we're going to go ahead and start with example 1. Suppose I had y equals 2/3 x to the 3/2, and x is less than or equal to 2 and greater than or equal to 0. Now, dy dx is 2/3 times 3/2 x to the 3/2 minus 1, which is 1/2. And so this is x to the 1/2. If I take 1 plus dy dx and square it, I get 1 plus x to the 1/2 squared, which is 1 plus x. So L is the integral from 0 to 2 of the square root of that result, the square root of 1 plus x dx. But that's 2/3 times 1 plus x to the 3/2, and I'm going to evaluate from 0 to 1. And so, therefore, L is 2/3 of. Now, when I plug the 1 in, I get 2 to the 3/2. When I plug 0 in, I get 1. So I'm just going to subtract 1. And so this is 2/3 times 2 square root of 2 minus 1. And that's how you do example 1. If we take a look at example 2, we get y equals x plus 4 to the 3/2. And here x is in between 0 and 4. So if I take dy dx, I get 3/2 times x plus 4 to the 1/2. So 1 plus dy dx to the second power is 1 plus. Now, I need to square 3/2 to get 9 over 4. And I'm going to multiply by x plus 4. Just like this. And so what I would do is distribute the 9/4 in. And so I get 1 plus 9 over 4x plus 9. 9/4 times 4 is 9. And so L is the integral from 0 to 4 of the square root of 9/4 x plus 10 dx. So I'm going to let u, because of that fraction, let's do a u substitution. So I'm going to let u be 9/4 x plus 10. du is 9/4 dx. So dx is 4 over 9 du. Now, when x is 0, u is 10. When x is 4, u is 19. And so this is going to be 4/9 the integral from 10 to 19 of the square root of u du, which is 4/9 times 2/3 u to the 3/2, and I'm going to evaluate from 10 up to 19. And so, well, this is going to be 8/27 times the quantity 19 square root of 19 minus 10 square root of 10. 19 to the 3/2 is 19 square root of 19. 10 to the 3/2 is 10 times the square root of 10. And that's how you do example 2. Note, if the curve has the equation x equals g of y, where c is less than or equal to y, which is less than or equal to d, and g prime of y is continuous, then L is going to be the integral from c to d of the square root of 1 plus g prime of y to the second power dy. So I'm still going to take the derivative, but just this time it's with respect to y. I'm going to square the result, add 1, take the square root, and then integrate from c to d this time. And then another way to write this is the integral from c to d of the square root of 1 plus dx dy squared. And then I'm going to integrate that result with respect to y. So it's same idea. You're still going to take the derivative. And with that in mind, I want to start on example 3. Suppose I give you this one. Suppose I give you x is y to the 4th divided by 8 plus 1/4. If you don't mind, I'm going to write this as 1/4 y to the negative 2. And y is between 1 and 2. So what I want you to do is find dx dy. Well, that's going to be 1/2 y to the 3rd minus 1/2 y to the negative 3. So that's just power rule, okay? Now, if I take dx dy and I want to square it, well, what ends up happening is I'm going to take and square 1/2 y cubed, which is 1/4 y to the 6th, minus 2 times 1/2 y to the 3rd times 1/2 y to the negative 3. And then I'm going to add 1/4 y to the negative 6. So this is 1/4 y to the 6. The 2's cancel, and I get minus 1/2 y to the 0, right? 3 plus negative 3 is 0, plus 1/4 y to the negative 6. But remember that y to the 0 is 1. So something to keep in mind. Okay. Now, 1 plus dx dy squared. Well, that's going to be equal to 1/4 y to the 6 plus 1/2 plus 1/4 y to the negative 6. Now, turns out what's interesting about this is that's going to be equal to 1/2 y to the 3rd plus 1/2 y to the negative 3 to the 2nd power. So this piece in the middle is a perfect square by design for this particular problem. And so L is going to be equal to the integral from 1 to 2 of the square root of, so I'm going to take 1/2 y cubed plus 1/2 y to the negative 3, and I'm going to square it and take the square root of that and then integrate with respect to y. And so it works out wonderfully. So you take the integral from 1 to 2 of 1/2 y cubed plus 1/2 y to the negative 3 dy. And so this is 1/2, I'll just do it this way, times 1/4 y to the 4th plus 1/2 times, now if I add 1 and divide, that's going to be -1/2 y to the negative 2, evaluated from 1 to 2. So this is 1/8 of 16 minus 1/4 times 2 to the negative 2. And then I'm going to subtract 1/8. And then I'm going to add 1/4. So this is 2 minus 1 over 16 minus 1 over 8 plus 1 over 4. Like this. Common denominator is 16, so that's the LCD. And so this is going to be 32 over 16 minus 2 over 32. It'll be 1 over 16 because that's the LCD. Minus 2 over 16 plus 4 over 16. So 32 minus 1 is 31. 31 minus 2 is 29. So it looks like the answer is 33/16. That's example 3. If we take a look at example 4, suppose I give you this one. Suppose I give you y equals natural log of secant x, and x is between 0 and pi over 4. So dy dx is 1 over secant x times secant x tangent x. But this is equal to tangent x. So 1 plus dy dx to the 2nd power is 1 plus tangent squared x. But remember that 1 plus tangent squared x is secant squared x, right? So I'm going to write this as secant squared x. So L is the integral from 0 to pi over 4 of the square root of the previous step. So it's the square root of secant squared x dx. But remember that we're on the interval from 0 to pi over 4. So this is the integral from 0 to pi over 4 of secant x. I don't have to worry about secant being negative on the interval from 0 to pi over 4. So I don't need any absolute values. okay? So this is the natural log of secant x plus tangent x, but we're going to evaluate from 0 to pi over 4. So this is natural log of secant of pi over 4 plus tangent of pi over 4 minus natural log of secant of 0 plus tangent of 0. Now, this is how I think, if it helps, cosine of pi over 4 is 1 over square root of 2. So secant of pi over 4, I just got to take the reciprocal. So it's square root of 2 over 1, right? And so this is natural log of square root of 2 plus 1. Tangent of pi over 4 is 1. And I'm going to subtract natural log of secant of 0 is 1. Tangent of 0 is 0. And so the answer here, natural log of 1 is 0, by the way. So the answer is natural log of square root of 2 plus 1. That's how you do example 4. If we take a look at example 5, suppose I give you something like this. X equals e to the y plus 1/4 e to the negative y, where y is between 0 and 1. So dx dy is e to the y minus 1/4 e to the negative y. So if I square this and add 1, I get 1 plus, and I'm going to square the previous step. So I get e to the 2y, that is, minus 2e to the y times 1/4 e to the negative y plus 1 over 16 e to the negative 2y. So these last three terms form a perfect square. Okay, now this is 1 plus e to the 2y minus a half, e to the 0 if you want, plus 1/16 e to the negative 2y. But that's e to the 2y. Remember that e to the 0 is 1. So this is plus a half plus 1/16 e to the negative 2y. But that's really nice because I claim e to the 2y plus a half plus 1/16 e to the negative 2y. Well, this is e to the y plus 1/4 e to the negative y, and this is raised to the second power. It's a perfect square. It's beautiful because now look what happens. L is the integral from 0 to 1 of the square root of this mess. In other words, it's the square root of e to the y plus 1/4 e to the negative y to the second power dy. So this is the integral from 0 to 1 of e to the y plus 1/4 e to the negative y, this whole thing dy. So this is e to the y minus 1/4 e to the negative y from 0 to 1. So you get e to the first minus 1/4 e to the negative 1 minus, put in 0, we get 1 minus a fourth. And so this is e minus 1 over 4e minus 3 over 4. And that is how, this is example 5. We can do one more, example 6. Suppose I give you this one. Y equals one over 4x squared minus 1/2 natural log of x, and x is less than or equal to 2, greater than or equal to 1. So I'm going to take dy dx, and I'm going to get 1/2 x minus 1 over 2x, which is 1/2 x minus 1/2 x to the negative 1. And so on this line, I'm going to take 1 plus dy dx squared. It's the same pattern. So I'm going to take 1 plus, and I'm going to emphasize it in this example. You're going to basically take 1/2 x minus 1/2 x to the negative 1 and square it, right? I'm going to take that and add 1. And so you get 1 plus 1/4 x squared minus 1/2 plus 1/4 x to the negative 2. So I'm just squaring out a binomial, essentially. But this is 1/4 x squared. 1 minus 1/2 is plus 1/2. And then I'm going to add 1/4 x to the negative 2. And this turns into 1/2 x plus, let's try that again. This is 1/2 x plus 1/2 x to the negative 1, and I'm going to square it. So L is the integral from 1 to 2 of the square root of 1/2 x plus 1/2 x to the negative 1 to the second dx. But this is the integral from 1 to 2 of 1/2 x plus 1/2 x to the negative 1 dx. So this is 1/4 x squared plus 1/2 natural log of x from 1 to 2. Okay? Now, when I plug the 2 in, I get 1 plus 1/2 natural log of 2. I'm going to take that answer and I'm going to subtract. Plug the 1 in for x, I'm going to get 1/4 plus 1/2 natural log of 1. But natural log of 1 is 0. And so the answer here for this question is 3/4 plus 1/2 natural log of 2. And that's going to conclude this video for section 8.1. We worked on, actually 6 examples finding arc length. Thank you.